All right, so today we're diving deep into antimatter.
Ooh, antimatter. Always a cool topic.
Yeah, but we're focusing on antiquarks specifically. We've got this really interesting essay, Antiquarks, Schlüsselteilchen in der Quantentechnologie.
That's by Yuriyo Schneepat.
Right, exactly. And it's going to help us figure out why these tiny particles are so important.
Not just important, but crucial to understanding the universe. And who knows, maybe even some wild future tech.
Right. So to start off, for anyone who maybe doesn't have quark in their everyday vocab,
Happens to the best of us.
what exactly are we talking about when we say antiquark?
Okay, so think of it this way. Quarks, right? They're like the tiny, tiny Lego bricks that make up protons and neutrons. Those are inside atoms.
The stuff everything's made of.
Exactly. Now, antiquarks, they're like the evil twins of quarks. Same mass, but they've got opposite properties, like flip switches. We call these quantum numbers.
Quantum numbers, okay.
Yeah.
And one of the biggest differences is electric charge.
You got it. If a quark has a positive charge, its antiquark buddy will have a negative one. Same strength.
So it's like a mirror image, but not quite.
More like a photonegative, I'd say. Now, you mentioned protons and neutrons being made of quarks. You're probably wondering, how does that work with antimatter?
Yeah, how does antimatter fit into the structure of, well, matter?
Well, protons and neutrons are three quarks hanging out together. But there's another particle called a meson.
Meson, okay.
It's made of one quark and one antiquark, a bit like a weird couple, but stable.
A quark and an antiquark together. But isn't antimatter supposed to annihilate matter?
It does, when they're the same type. Well, but in the meson, they're bound together by the strong force, so they chill. And studying these pairs, it's like peeking into how the strong force works, one of the fundamental forces of the universe.
That's fascinating. So we've got these quarks and antiquarks. Now, the essay mentions different flavors of quarks. Are there different types of antiquarks, too?
Absolutely. Schneepat lays it all out. 6 flavors of quarks. Up, down, strange, charm, bottom, and top. And for each one, there's an anti-flavor. And up, anti-down, you get the picture. Each antiquark has the opposite electric charge of its quark twin, but the same mass.
Okay, I'm trying to keep up. So 6 flavors of quarks, 6 flavors of antiquarks. What about their charges and masses specifically? I'm trying to wrap my head around these, abstract particles.
Sure thing.
Yeah.
So the up quark, it's got a charge of plus 2/3 of the elementary charge, or E. The anti-up has minus 2/3 E. Down quark, minus 1/3 E, anti-down, plus 1/3 E.
All right, got it. The opposites.
Now, strange is also minus 1/3 E, so anti-strange is plus 1/3 E. Now we get to the heavyweights. Charm is plus 2/3 E, anti-charm minus 2/3 E, bottom minus 1/3 E, anti-bottom plus 1/3 E, and lastly, the top quark, plus 2/3 E, anti-top minus 2/3 E.
Whoa, okay. I'm seeing a pattern with the charges. But what about their masses? You said they have the same mass as their quark counterparts, right?
Yeah, but the masses themselves are all over the place. Up and down quarks are the lightest, around a couple of megathelium.
Yeah.
But the top quark, it's a monster. Around 173 GeV on both quark and antiquark. That's like 80,000 times heavier than the up quark.
80,000 times. That's a huge difference.
It is, and Schneepat kind of hints at this. But that mass difference plays a big role in how they behave and how we study them.
So we've got these antiquarks. They're the opposites of quarks, but with the same mass. Why are they so important to physicists? I mean, are they more than just the negative version of quarks?
Oh, way more. They're fundamental to the standard model of particle physics.
Yeah.
It's like the rule book for all the known particles and how they interact.
Except gravity, right?
Right, gravity's doing its own thing. But anyway, antiquarks, they help us test how the strong force works, especially when we look at mesons. And when we smash particles together at super high speeds, like in the Large Hadron Collider.
Yeah, where they found the Higgs boson.
Exactly. Antiquarks pop up there, giving us clues about what's happening at these crazy high energies. They might even point us towards physics beyond the standard model, stuff we haven't even dreamed up yet.
Okay, so they're crucial for understanding what we know now. But the essay also talks about how antiquarks might be important for future tech, specifically quantum technology. Now that's where it gets really interesting.
Right, that's where things get wild. We're talking early stages here, but the potential is huge. We already use antimatter in a way, with PD scans, positron emission tomography.
PET scans, those are for medical imaging, right?
Yep, and they use positrons, which are the antimatter version of electrons. When a positron meets an electron, boom, they annihilate each other, releasing energy we can detect and use to make detailed images of the inside of your body.
Wow, I never realized PT scans use antimatter. That's incredible.
It is, and it shows that antimatter already has real-world applications. Schneeppert also points out how studying antiquarks is helping us build better particle accelerators, which are these massive machines that smash particles together.
Because you need insane amounts of energy to create and study antiquarks, right?
Exactly, and pushing those limits benefits all sorts of scientific fields, not just particle physics.
Makes sense. What other future tech is on the horizon?
Well, there's a lot of buzz about quantum computing. It's still very early days, but the unique quantum properties of quarks and antiquarks, things like their spin and color charge.
Color charge, that's a weird one.
It is. But these properties might be the key to building super powerful quantum computers. Imagine using the building blocks of matter and antimatter to power computers.
That's some serious sci-fi stuff.
It is, and Schneeppert acknowledges that there are massive challenges to overcome. But another even more futuristic idea is antimatter storage. Imagine harnessing the insane energy density of antimatter.
Like in Star Trek?
Kind of. If we could figure out how to safely store it, it could revolutionize energy production. We're talking interstellar travel even.
So I'm like a long way off.
Definitely. But the physics is real. Now, the essay also touches on the history of how we figured all this stuff out. Guys like Gell-Mann and Zweig, they were pioneers.
They came up with the idea of quarks, right?
Yep, back in 1964. They were looking at all these new particles being discovered and thought, maybe they're not so fundamental after all. Maybe they're made of even smaller bits, which Gell-Mann called quarks.
So how did people react to that? It sounds pretty radical.
It was. People were skeptical because quarks have fractional electric charges, something no one had ever seen on its own.
So how did they prove it? Was there a big eureka moment?
Not really. It was more like a slow burn. In the late 60s and early 70s, they did experiments where they smashed electrons into protons.
At that big accelerator in California, SLAC.
Yeah, SLAC. And they found that protons weren't solid. They had internal structure. It was like, bam, quarks are real. Then, in the 70s, they came up with quantum chromodynamics, or QCD, which explains how the strong force holds quarks together.
So they had the theory and the experiments to back it up.
Right. And then in 1995, they found the top quark, the last one on the list. That was a big win for the Standard Model and really solidified the whole quark picture. Schneeppert mentions this as a huge moment in particle physics.
It's amazing how far we've come. Now, what mysteries are left to solve? What can antiquarks help us figure out in the future?
Oh, tons of stuff. Schneeppert touches on some really exciting frontiers. One is the hunt for exotic hadrons. We know quarks like to hang out in groups of 2, like in mesons, or 3, like in protons and neutrons.
Those are called baryons.
They got it. But what about groups of 4 or 5 quarks? Those are called tetraquarks and pentaquarks, and there's growing evidence they exist.
So like a whole new class of particles.
Potentially. And by studying them, we can learn even more about the strong force and how quarks get along in bigger groups.
So what else is out there? What other big questions can antiquarks help us answer?
One of the biggest is the matter-antimatter asymmetry problem. See, according to what we know about the Big Bang, equal amounts of matter and antimatter should have been created. But look around. Everything's made of matter. Where did all the antimatter go?
That's a pretty big question.
It's one of the biggest in cosmology. And Schneeppert mentions this too. One idea is that there's a tiny imbalance in the laws of physics called CP violation. Basically, matter and antimatter don't behave exactly the same way.
So this tiny difference could explain why we exist.
It's mind-blowing, right?
Yeah.
And to study CP violation, we need to look at how particles containing quarks and antiquarks decay, especially those with bottom and charm quarks.
So by studying antiquarks, we're not just learning about tiny particles, we're trying to figure out why the universe is the way it is.
Exactly. And finally, Schneeppert hints at something even bigger. We know the Standard Model is really good, but it doesn't explain everything, like gravity. Some physicists think there might be a deeper theory out there, a theory of everything that explains all the forces. And guess what?
Antiquarks are going to be part of it.
You bet. Studying antiquarks might give us clues about this ultimate theory, or even show us that quarks and leptons, like electrons, are connected in a way we don't understand yet.
So in this deep dive, we've gone from the smallest building blocks of matter to the biggest mysteries of the universe. And it's all thanks to Schneeppert's essay and the amazing world of antiquarks.
It's been a wild ride. We've seen how antiquarks are essential for understanding how matter works, how they might be the key to futuristic technologies, and how they can help us answer some of the biggest questions about the universe.
And we've seen how the discovery of quarks and antiquarks, from the initial theories of Gell-Mann and Zweig to finding all 6 quark flavors, shows just how powerful human curiosity and scientific exploration can be.
Absolutely. The work on exotic hadrons, figuring out the matter-antimatter asymmetry, and the search for a theory of everything, it all shows that antiquarks are at the forefront of modern physics. They're helping us push the boundaries of what we know.
This has been an incredible journey into the world of antiquarks. For anyone wanting to learn more, I'd say dive into the standard model of particle physics, or even just read more about antimatter in general. There's a whole universe out there, and thanks to physicists like Jörg O. Schneepatt, we're getting closer to understanding it every day.